Now we are looking at your face.
Okay, so share screen. Okay, and okay, share.
Okay, working, and now you should just put it in full. Perfect. Okay, everything is working. You can go ahead, please.
Okay, well, I would like to thank the organizers for inviting me to talk here. It's been a very interesting conference. I would like to talk about the production of X3872 as a function of the multiplicity. And this is work I've been doing with Li Ping He and Kevin Ingles, students at Ohio State University, and with Jun Zhang, who's...
Sorry, can you just move a bit away from the microphone? You are saturating.
Okay.
Thank you.
All right. Is that better? Okay. Also, I'd like to acknowledge research support from the U.S. Department of Energy. I was hoping to press down arrow and get the next slide. Whoops, I guess it just delayed. Okay. All right, so exotic heavy hadrons. The heavy says that it contains a charm or bottom quark. Exotic means, to me, that it's not predicted by the quark model. So, for example, a tetraquark meson or a pentaquark baryon would be a exotic hadron. Now, the dozens of exotic heavy hadrons have been discovered, and it all began with the X3872 in 2003. And it's a serious challenge to particle theory to explain the exotic heavy hadrons that have been discovered and to predict those that remain to be discovered. I'm going to focus on the X3872 with the hope that understanding this particle may provide insights into the other exotic heavy hadrons. So the X3872, it's also known as the Chi-C1 3872. It was discovered by the Bell collaboration in 2003 at an E+E- collider through the decay into J psi pi plus pi minus, confirmed by the CDF collaboration in a PP bar collider. Its quantum numbers were definitively determined by LHCb collaboration in 2013 to be 1++. Its mass, even the first discovery, showed that its mass was extremely close to the d star 0, d bar 0 threshold. Since that time, the measurement of the mass has improved and the measurement of the threshold has also improved. And the most recent measurements from the LHCb collaboration tell you that the difference of the energy, difference between the mass and the threshold is minus 0.07 plus or minus 0.12 MeV. And that tells you the binding energy relative to that threshold is less than 0.22 MeV at the 90% confidence level. It's extremely weakly bound. LHCb collaboration also measured its width. The width has to be qualified by measured the width assuming a Bright-Wigner parameterization, and it's about 1 MeV. If you take into account the presence of the nearby threshold, you can get the width determined by the pole in the propagator. It might easily be a factor of 3 or 5 smaller. There are 7 observed decay modes, and that makes this X3872 is the heavy exotic hadron by which the most information is available. And we would like to be able to exploit that. Okay, oops, wrong way. So what is the X3872? Well, I claim that given the information that the quantum numbers are 1++ and the binding energy is extremely tiny, it must be a loosely bound charm-meson molecule. It must be an even charge conjugation mixture of d star 0, d bar 0, and d0, d bar star 0, plus a small admixture of d0, d bar 0, pi 0. And this molecule has universal properties that are determined by the binding energy. For example, the wave function has the form e to the minus gamma r over r, and from that wave function you can calculate the mean separation of constituents. And you will find, this gamma, by the way, was the binding momentum. The mean separation is 1/2 gamma. That tells you if given that the binding energy is less than 0.22 MeV, the mean separation must be greater than 4.8 Fermis. So it's really an amazing hadron whose size and whose radius is an order of magnitude larger than most hadrons. So this tells you what it is. Now, what is maybe a more relevant question for most people is, what would the X3872 be if not for that fine-tuning of its mass to this threshold? It could be a p-wave charmonium state with constituent CC bar. It could be an isospin zero charm-meson molecule, which is which contains both neutral and charged charm-mesons. It could be an isospin 1 compact tetraquark, whose constituents are a tetraquark or a diquark and an anti-diquark. Or it could be something else, but in all cases, the X3872 is transformed to this very large charm-meson molecule consisting of neutral charm-mesons by the resonant couplings to the charm-mesons at that threshold. I'm going to turn now to the production of X at a Hadron Collider. There are two very distinct production mechanisms that can be disentangled experimentally. One is the production by B-hadron decay. In this case, the decay products emerge from a displaced secondary vertex, and the number of charged particles will be less than, almost always less than 10. An example is the discovery decay mode will give you 5 charged particles, a K plus, a pi plus pi minus, and a mu plus mu minus. The other category is prompt production by QC mechanisms. And in this case, the decay products emerge from the primary collision vertex. In this case, the number of charged particles, let's say at the LHC, would be, the number of charged particles would be probably in the hundreds, and the number of charged particles per unit rapidity could easily be in the tens. Now there's a very nice measurement by LHCb collaboration this year of the production of the dependence of the production of X in PP collisions on the Hadron multiplicity. What they measured was the ratio of the cross section times branching fraction into J psi pi plus pi minus for X and for psi 2s as a function of the number of tracks in the vertex detector. And the data is shown here. The lower points here, the black arrow point, the black data points are from B decay, and the upper data points here, the red ones, are from prompt production. And there seems to be a small increase as a function of multiplicity in the production from B decay, but it's not statistically significant. On the other hand, for prompt production, there is a significant decrease in the ratio as a function of the number of charged tracks. In the confidence proceedings where this data was presented, they suggested that this was consistent with the interpretation of X as a weakly bound charm-meson molecule. This conclusion was challenged in a subsequent paper, subsequent paper by Esposito et al. They used the comover interaction model to predict the ratio of the number of X to psi events as a function of the charged hadron multiplicity. And these are their results in this graph down here. This red band is their prediction of what the dependence would be for a tetraquark state. This blue curve is their prediction for what it would be if it was a molecule. And what you see is that the red band goes right to the data. The blue, the very, very new band just crashes down to 0 very quickly. And it basically says that LHCb should not have seen any X's except perhaps the very smallest multiplicities. So their conclusions is that the LHCb results clearly support X being a tetraquark state, and they strongly disfavor the molecular interpretation. And what I would like to do is challenge this conclusion. One thing I would like to point out is that the statement is about it being they're trying to compare a compact tetraquark state, which is a fictitious thing that cannot exist. A tetraquark, if it was tuned to the binding energy of the X, it would be transformed into a large object that would be more interpreted as molecule. And so what I will claim is that their prediction for the molecule is way off the mark. So let me begin by telling you what this comb-over interaction model that they used was, or what it is. Okay, I'm not getting any, oh, okay, there we go. Okay, it originated back in 1996 by several authors who are describing the suppression of J psi and psi 2s in proton-proton, proton-nucleus, and nucleus-nucleus collisions. And the mechanism in this model is the breakup of the CC bar meson by collisions with comovers. And these comovers you can interpret as gluons or perhaps as pions. In 2018, Ferrero and Landsberg developed a more elaborate version of this model to describe the suppression of upsilon 2s and 3s compared to upsilon. In this more elaborate version, the comovers are given a momentum distribution that's a Bose-Einstein distribution in the rest frame of the BB bar meson that has an effective temperature that they determine by matching experimental results to be 250 plus or minus 50 MeV. They also they assume that the cross section for the breakup of the BB bar meson was the geometric cross section, pi times r squared, where r is the mean separation of the constituents. And so this is basically what Esposito and all, what they used. They applied this comb-over interaction model to the X and to the psi prime. The survival probabilities of these mesons in this model as a function of charge hadron multiplicity is given by this exponential suppression. It depends quite dramatically on the number of charged particles per unit rapidity. There are a couple phenomenological parameters, sigma pp and rho, but there's also then this factor average V sigma, which is the breakup reaction rate averaged over the comovers. And they followed Ferrero and Landsberg by assuming that this average breakup reaction rate was just a geometric cross section where it's pi r squared, where r is the mean separation of constituents. For the psi prime, that mean separation is roughly 0.45 Fermis, separation of the C and C bar. For the X, they suggested the mean separation in the compact tetra, if it's a compact tetraquark, would be 0.65. If it's a weakly binding charm-meson molecule, the mean separation can be calculated from the binding energy. And they took a binding energy of 116 keV and got 6.6 Fermis for the radius, which you can see is an order of magnitude larger than what they assumed for the compact tetraquark. If the radius is an order of magnitude larger, the average V sigma is 2 orders of magnitude larger, and this factor is occurring as a prefactor inside the exponent, and so it gives you a huge suppression. Having 2 orders of magnitude larger factor here gives a huge suppression, and that's why they got that this cross section just crashes immediately down to 0 as a function of multiplicity. Okay, I'm going to take a slight diversion. I want to discuss how you would actually calculate this breakup reaction rate. The diversion is to an effective field theory called XEFT that was developed by Fleming, Kusunoki, Meehan, and von Kolk back in 2007. It's an effective field theory for charm-mesons and pions. XEFT describes these combinations of charm-mesons and pions, d star d bar, or d bar star, or d bar pi, and X, all with total energy near the d star d bar threshold. Now, this effective theory can also describe a more additional configurations with additional charm-mesons or additional pions. In particular, it can describe the sector of QCD containing d star d bar star, d star d bar pi, dd bar star pi, dd bar pi pi, and x pi, all of them with total energy near the d star threshold. And so you can actually calculate the cross sections for the breakup of X in this effective field theory through the scattering of a low energy pion. I want to just mention some other related work that, a few years back, I developed a Galilean invariant formulation of XEFT that exploits the approximate conservation of mass in d star into d pi transitions and simplifies many aspects of XEFT. My collaborators and I recently developed an improved formulation of this effective field theory. Another thing I should mention is that there are suggestions that there are large NLO corrections in XEFT, some work by Dai, Wu, and Meehan, but we plan to use this Galilean invariant version of XEFT to show that, in fact, the large NLO corrections are just from a unwise organization of the problem, and that NLO corrections are, in fact, very small in this effective field theory. Okay, so let's go to pi-x breakup scattering. So XEFT can be used to calculate the pi-x breakup scattering when the pion momentum is small. It'll go through a diagram like this, where x plus pi goes to d star, d star. You can calculate the cross-section as a function of the kinetic energy of the pions, and you'll find slightly different thresholds for the two cases, pi plus and pi zero. And in both cases, there's a very, very large resonance near the threshold. The cross-section is dominated by these cross-sections are dominated by a d-star resonance. They rise into millibarn, into the millibarn region, but the contributions to the reaction rate that we really want, the pi-x reaction rate.
Let me interrupt you.
Yes.
It's difficult to understand what you're saying because your microphone is saturating.
Okay.
Can you speak more quietly or move away from the microphone?
Okay. Okay, I'll just move back further. Is that better, or is it further
Yes.
more?
Thank you. Thank you.
Okay. All right. All right. So anyway, we can calculate the pi-x breakup cross sections, but these low energy resonances in the cross section do not contribute significantly to the reaction rate. They give something in the 15 microbarns region if I use that comover interaction model with an effective temperature as determined by Landsberg and Ferrero. But we can we can also describe the effects of high energy pions, and that's simply because the high energy pions will scatter from the constituents. And if a high energy pion scatters from any of the constituents of the X, it will break up. It will contribute to breakup cross section. And so the breakup cross section will be the sum of the constituents, sum of the cross sections for the constituents multiplied by their probabilities. Well, these cross sections at high energy are beyond the range of validity of XEFT. We can estimate reaction rates from other people's work on the scattering of high energy pions with charm-mesons. There's a paper from Lim D and Co back in 2000, which considered hadrons in thermal equilibrium at a temperature at temperatures up to 200 MeV, and they calculated the reaction rates average over thermal distributions for pi d and for pi d star as functions of the temperature. And in particular, you can take the results for pi d and pi d star and insert them into this formula for the breakup cross section, and find their result is that the cross section is 26 plus or minus 11 millibarns at a temperature of 200 MeV. And this is large enough to affect the reaction rate. So I'm going to, since the only thing I have, I am going to approximate the reaction rate we want, which is the breakup reaction rate of X in the X raised frame at a temperature in this range determined by Landsberg from bottomonium data by the results of these people in the thermal frame at the highest temperature that they did, which was 200 MeV. But if I do that, we can predict the reaction rate. And so here are some results. So first of all, the reaction rates for X and psi breakup from Esposito. Their result for psi based on the geometric cross section was about 5 millibarns. For X, if it's a tetraquark, it was 11 or 12 millibarns. In the case of a molecule, it was 2 orders of magnitude larger, 1200 millibarns. If I take those results from the 2000 paper on pi d and pi d star collisions, what we get is 26 plus minus 11 millibarns. And so I just inserted these results into the formula for the survival probabilities, and these are the resulting curves you get. The result of Esposito, if X is a tetraquark, would be this red range down here. If you go back and look at the results in the paper, they actually have a curve that runs right through the data with an error bar range that was never stated clearly how they get the result or what their error bar range was. But this reaction rate is something that occurs as a prefactor in a rapidly decreasing exponential. And it's not very hard to move this range over on top of the data just by adjusting parameters or adjusting the way you do things. If we take this estimate of the reaction rate from scattering off the constituents of the molecule, we get this blue result. It's well below the data, but again, this reaction rate is the prefactor in an exponential that's falling rapidly, and it's not hard to move this prefactor up. If this curve that's this almost vertical blue curve is the result of Esposito if it's a molecule, and it's crashing down because the cross section is 100 times larger than the other cases. Anyway, this would be the punchline. They're still preliminary results that we have to understand how they actually arrived at a cross section that goes through the data from this, and we have to see what else can be done. But anyway, it's clear that the reaction rate, the multiplicity dependence, if it's a weakly bound molecule, does not crash down to 0 as what they predicted, but it does decrease more gently. Okay, so let me just summarize. There's 3 points I tried to make. One is that given the quantum numbers and the binding energy, you can conclude that X must be a loosely bound charm-meson molecule with universal properties determined by its binding energy, and its constituents are simply d star 0 and d bar 0. If not for the fine-tuning of its mass to that threshold, it could have been any number of things: a p-wave charmonium state, or an isospin 0 charm-meson molecule, or an isospin 1 compact quark, or something else. But it is transformed into this charm-meson molecule with neutral charm-mesons by the resonant interactions with the charm-mesons at this threshold. So that's one point. Another point is that the X can be broken up by scattering with comoving pions. For low-energy pions, the breakup cross-section can be calculated using XEFT. For high-energy pions, the breakup cross-section is dominated by scattering from the constituents, and so if you had an accurate understanding of the cross-section of the cross-sections for pions and charm-mesons at high energy, you could predict the reaction rate in this comoving interaction model and predict the multiplicity dependence. Now, contrary to the assumption of Esposito et al., the pi x breakup cross-section is insensitive to the tiny binding energy of X. once you have high energy, it doesn't care what the binding energy is, it scatters off the constituents. So it doesn't matter that the X has this huge mean separation of constituents that is larger than 5 MeV. It's just irrelevant to the reaction rate. Finally, the prompt production of X in PP collisions has been studied by LHCb, and they've observed a decrease in the ratio of X to psi 2S with the increasing multiplicity. The dependence on the multiplicity predicted by this co-mover interaction model is roughly compatible with the charm-meson molecule. It is also compatible with this fictitious compact tetraquark that does not couple to the charm-mesons of the threshold, as shown by Esposito et al. So in the future, we would hope to develop a quantitative description of the dependence on the multiplicity of the production of X in PP collisions, and then apply it to proton nucleus and also nucleus-nucleus collisions. So I thank you for your attention.
Thanks a lot, Eric. Thanks also for keeping the time. Are there any questions? So we have two questions. Let's start with Oleg.
Thanks for interesting talk. And I would like to ask, is it possible somehow to accommodate to the molecule picture the existence of the state of a partner with different charge parity, which appears in tetraquarks? I am asking also because at COMPASS there are some indications of appearance such state with different charge parity in lepton production.
Okay, the fact that this is this very large weakly bound molecule comes from this extremely tiny binding energy, which is more than an order of magnitude smaller than the different isospin splittings. And so the fact that this is so close to a threshold, if you had charge partners,
charge parity partners, I mean, isn't it possible to get a molecule with negative charge parity?
Negative charge, this is 1++, and you would like 1 plus minus?
Yeah, plus, yeah. Is it possible to get such state also as a molecule?
I would say it's possible, but it's not something that you can predict from the existence of the X.
I see.
This is very special, like extremely tiny binding energy.
I see. I see.
Okay.
So this means that positive charge parity is definitely preferred for the molecule, right?
No, it's the fact that with 1++ quantum numbers, there's an S-wave coupling to the charm-mesons of the threshold.
Yeah.
Anytime you have an S-wave coupling and you tune close up to the threshold, you will get this very large extended object, this weakly bound molecule.
I see.
Let's move on to the next question.
Okay,
Peter?
Yeah, hi, Eric. So I was wondering, you have a significant decay to J-psi states. So if you have a molecular picture, how do you understand the decay into J-psi or psi prime?
It just comes from the fact that the wave function at the origin, this wave function at the origin is divergent, which means it is sensitive to the behavior at very short distances. And it's through that the fact that there's a large wave function to the origin that you can have a transition of DD star in order to J psi plus other stuff.
Mm-hmm. But that's, you cannot predict with an EFT because that's beyond the reach, right?
Yes, this is the branching fractions into various J psi decay modes are not universal properties determined by the binding energy.
Mm-hmm. Okay, thank you.
Okay, Rob, you're next.
Hi, Eric. I know you didn't speak about it, but what is your opinion about the recently discovered states with 4 charmed quarks?
Well, it seems that there are definitely some states that are tetraquarks, and so I would, for me, that would raise the possibility that if it was not close to the threshold, that it would be a compact tetraquark as opposed to the other possibilities. But the properties of the X, I mean, the universal properties of X don't shed any light on that.
Yeah, yeah. No, I understand. It's just hard to understand why CC bar and CC bar should stay together and not just fly apart. But okay, very good. Thanks.
Okay, I think in the interest of time, we really have to move on. Thanks a lot for everyone who participated in the discussion. And thanks a lot, Eric, for the very nice talk. Let's move on to Michael Strickland.
Can you hear me?